This lecture is going to go over a noble gas electron configuration. So now that we've gone over electron configuration, we should know that this is really just a shorthand notation to write out all the orbitals that describe all of the electrons in an atom. Reminder that electrons will be described by orbitals to get the lowest possible energy. Each orbital can describe up to 2 electrons. In the order of orbital energy, we're always going to start with the lowest energy, which is a 1s, then 2s, 2p, 3s, 3p, 4s, 3d. So this is the order of orbital energy that we would follow. If we have to put electrons in degenerate orbitals, it's going to be lower in energy to have electrons in unpaired and separate degenerate orbitals than to be spin paired. And so, for example, when we have something like nitrogen, we would do 1s2, 2s2, 2p3. Those 3 electrons in a p orbital are actually in 3 different p orbitals, which we can describe as shown here in our orbital energy diagram. So a couple other things we want to point out about our electron configurations. One of the most important differentiations we can make is we're going to differentiate between 2 types of electrons, valence electrons and core electrons. And the reason we make this distinction is valence electrons are responsible for all of chemical reactivity. So it's going to be really important from here on out in chemistry to understand how many valence electrons are present in a given molecule. These valence electrons are, by definition, the highest energy electrons. So these are the electrons described by the highest principal quantum number. Core electrons are the electrons that are closest to the nucleus. In other words, they're all the electrons that are not valence electrons. So for example, in carbon, the electron configuration is 1s2, 2s2, 2p4. So carbon's valence electrons are shown here in this box. They're all of the valence electrons in the second shell because 2 is the highest principal quantum number. So carbon has 4 valence electrons and 2 core electrons. Sodium, whose electron configuration is 1s2, 2s2, 2p6, 3s1, has only a single valence electron. We would only take the electron in the third shell, which is the 3s1, so only 1 valence electron here. One of the nice things about writing electron configurations is we can develop even another shorthand and write what we call the noble gas electron configurations. And to illustrate this, if we were to write out the electron configuration of argon, which has 18 total electrons, and calcium, which has 20 total electrons. So argon would look like this. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. And one of the things to note is argon is a noble gas. So this electron configuration represents a full shell of electrons. We've filled up the whole periodic table to the end of that third row. Calcium has 20 electrons, so it has 2 more electrons than argon. And so one of the things we see is the 1s2, 2s2, 2p6, 3s2, 3p6 is exactly the same as argon. So this part of the electron configurations is exactly the same as argon. And the only thing that comes next are the valence electrons. So here's the valence, the 4s2. So one of the things we can do is we can rewrite the electron configuration of calcium, and we can write it as calcium is argon in brackets 4s2. And the key in this shorthand is that we're always going to take the previous noble gas. So if you find calcium on the periodic table, go up 1 row and all the way to the right to the noble gas. The previous noble gas is argon. So we're going to put argon in brackets, and that argon in brackets represents this portion of the electron configuration, right, which we said is the same. So we can just simply write argon, which we know means a full shell up to there, And then after that, we just write whatever's left over. What are the valence electrons? In this case, 4s2. Thank you.